Welcome back to the deep dive. Today, we're jumping into the world of AI, specifically a domain that gives us some of the most stunning breakthroughs: deep reinforcement learning, DRL.
Right. These are the algorithms that can master the game of Go, that learn to control complex robots. They really can seem like magic.
They do. But our source material today points out that behind that magic, there's a huge scientific problem, a kind of systemic crisis in reproducibility.
It's a massive problem.
Yeah.
You have these high-profile papers claiming state-of-the-art performance.
Yeah.
But then other researchers, third parties, they try to run the code with the exact same setup
And get nothing.
or get wildly different, completely unusable results. It's a real issue.
And that's the core of it. DRL isn't just part of the general machine learning reproducibility problem, it's like an extreme case. If you, as a researcher or practitioner, can't reliably replicate a finding, then you're stuck.
Completely stuck. You have no way of knowing if that big breakthrough was genuine or if it was just a fluke, a lucky accident in one specific lab setup.
Precisely. And that threatens the entire field. It stalls progress because you have people wasting time trying to build on results that are fundamentally unstable.
So our mission today is pretty clear. We're going to dissect why DRL is so uniquely vulnerable to this, so much harder to reproduce than other AI models.
And crucially, we're going to lay out a concrete framework, 3 pillars, really for getting the field back onto a foundation of real scientific rigor.
It starts with understanding the fundamental architectural weak point in all of DRL.
Okay, let's unpack that. When people think about standard machine learning, something like, I don't know, image classification, the process is pretty stable. Why is DRL so volatile?
It all comes down to the data distribution. In supervised learning, it's stable because you're training on a fixed data set.
You have your 10,000 labeled cat photos, and that's it. That data set doesn't change.
Exactly. Your model slowly gets better based on that stable, unchanging pool of data.
But
in DRL, the agent is constantly interacting with this world. So it faces what we call a non-stationary training distribution. The agent itself is generating the data. Every action it takes modifies the environment, which then modifies the very next piece of data it sees.
it's a feedback loop.
A constant feedback loop. Agent to action, action to environment, environment to new data, and that data feeds right back into the agent.
So how does that loop turn into an amplifier for randomness?
Well, think about it. If you have a tiny inconsistency in a stable system, like a small floating point error or a random number generator that's off by a tiny amount, it gets averaged out over millions of samples.
It just becomes noise.
It just becomes noise.
Yeah.
In DRL, not a chance. Those tiny inconsistencies, especially early on, they aren't canceled out. They trigger a fundamental divergence in the training path.
The butterfly effect.
Amplified, yeah. One agent might explore path A and see dataset X.
Hmm.
Another agent, with a minuscule difference at the start, explores path B and sees a totally different dataset, Y.
And suddenly you have 2 completely different learning histories, even though they started from almost the same point.
Exactly. And that makes third-party replication a nightmare, because you can't even guarantee 2 runs will see the same parts of the world.
Okay, so the system is almost designed to amplify tiny errors. That brings us right to the first major technical barrier, what the sources call algorithmic brittleness.
This is what I like to call the hidden recipe problem. Everyone knows DRL performance depends on hyperparameters, like learning rate. But what the research is showing is that success often hinges on a huge number of tiny implementation details that almost never get reported in the papers.
It's like a baker giving you a recipe with flour and sugar, but they forget to mention sifting the flour 5 times or using butter at a specific temperature.
That is a perfect analogy. You miss one of those hidden steps, and the whole thing collapses. And there's a really shocking example of this with the PPO algorithm, proximal policy optimization.
Which is, that's a go-to standard for a lot of DRL work, right?
It is. And yet, one of our sources found there are nearly 37 separate implementation details that critically affect its performance.
Wait, 37? Not 4 or 5, but 37 tiny engineering choices that could make or break a replication attempt.
That's right. And we're not talking about the main hyperparameters. We're talking about things like value clipping schedules, how rewards are normalized, really subtle stuff.
That's insane. So the successful code bases, things like CleanRL or Stable Baselines 3.
Right. They've become so popular, not because they invented a new algorithm, but because they meticulously went through and cataloged all this tacit knowledge that was just missing from the original papers. They baked the hidden recipe into the code.
So the state of the art isn't really the paper anymore. It's the community vetted code. This has to change how we measure success. We have to get beyond just reporting one peak score.
We absolutely have to. We need real rigor in analyzing hyperparameter sensitivity. We need to know if an algorithm is genuinely good or if the researchers just got lucky with one specific combination of settings.
So, what metrics should we be demanding instead?
The sources are clear on this. You need to report two scores to show an algorithm can generalize. First is the per environment tuned score.
That's the best you can possibly get on one task after tuning everything specifically for it, your maximum potential.
Exactly. But then you also need the cross environment tune score. This is the performance you get with one single fixed set of hyperparameters, but you run it across multiple different environments.
Ah, I see. So if that cross environment score just tanks.
Then you know your algorithm isn't robust. It's a fragile, hyper-specific solution, not a general breakthrough. It's a fantastic measure of rigor.
Okay, so the algorithms themselves are brittle. Let's move to a source of randomness that's totally outside the kind, the hardware. System non-determinism.
This one is particularly insidious because it happens at such a low level, usually on the GPU. We use parallel processing for speed, but some operations like summing up a bunch of numbers at the same time using a function like atomic add are inherently non-deterministic.
Meaning the order of the calculations can change slightly each run, and that changes the final number by a tiny amount.
A tiny, tiny amount. But remember, DRL's non-stationary nature. Those tiny errors don't get averaged out. They compound immediately.
It's that domino analogy again, a tiny, non-deterministic flip at the very beginning.
Triggers a cascading effect that results in a completely different learned policy by the end of training. One agent learns to solve the maze, the other just learns to crash into the first wall.
So achieving true determinism is a mandate. You have to control all the sources of randomness, even the ones in the hardware.
Everything. GPU operations, environment seeds, network initialization, the order of your data mini batches. If you don't control the system, you can't control the science.
This whole issue of randomness leads us to another major methodological flaw, the random seed paradox. What are researchers getting wrong with seeds?
They're misusing them, fundamentally. Often, a researcher will just fix a single seed and say, see, it's replicable. But even worse is the temptation to cherry pick.
The lucky seed.
The lucky seed. You run the experiment with 20 different seeds, find the one that gives you that amazing chart-topping result, and then you only report that single score.
And you're presenting a statistical outlier as if it's the typical expected result.
It's deeply misleading. The real scientific purpose of a seed should be for debugging. The actual goal isn't perfect replication of one run, it's conclusion stability.
Conclusion stability. What does that mean in practice?
It means that if I claim algorithm A is better than algorithm B, that conclusion should hold up across, say, 10 or 20 independent runs with different seeds. The conclusion should be stable, even if the exact mean score varies a bit.
So we stop chasing a single trophy score and start looking for a statistically robust outcome.
That's the only way forward. Rigor means you have to report performance distributions. You show the mean score, yes, but you show it alongside a measure of variation like error bars or a 95% confidence interval.
And if your reported improvement is smaller than your error bars,
Then you haven't actually proven anything. You haven't moved the field forward.
and as we scale up DRL, this problem gets even harder, right? When you start using distributed systems, actor-learner models across hundreds of CPUs.
Oh, it gets so much worse. As soon as you move to massive asynchronous parallelization, you introduce all these new timing and synchronization issues that just destroy determinism.
Yeah.
The key failure mode here is something called policy staleness.
Policy staleness. Tell me about that.
So in a distributed setup, you have actors out there collecting data and one central learner that's updating the policy. If the learner updates super fast and the actors are all running at their own pace, the data that comes back is a total mess.
Because it contains experiences generated by multiple different versions of the policy.
Exactly. The data's composition becomes chaotic and completely non-deterministic.
Yeah.
And the nature of that chaos depends entirely on the relative speeds of your CPUs and network.
So my experiment on a small machine will get a different result than yours on a massive cloud cluster, even with the same code.
Precisely. Your hyperparameters alone become meaningless. The rush for maximum speed directly creates instability.
So we need an architectural fix, something that prioritizes deterministic data flow over just raw, chaotic speed. What are our sources suggesting here?
Well, platforms like Cleanaba are showing the way. They focus on two key principles. First, You have to decouple the hypoparameters from the hardware.
Meaning you separate the logic of the experiment from how many CPUs you happen to be running it on.
Yes. So moving your experiment from your laptop to a supercomputer only changes the speed of training, not the underlying learning dynamics.
And the second principle.
Enforced deterministic data flow. They use a synchronization gate, a discipline mechanism to make sure the learner only updates the policy using data collected from a consistent, known version of that policy.
So you might say the policy at step I can only be updated using data collected by the policy from step I-1.
Exactly. You build in a tiny intentional delay, you sacrifice a little bit of maximum theoretical speed, but you gain guaranteed consistency. You eliminate the staleness problem entirely.
That's really clever. It's engineering for robustness, not just for speed.
And in science, robustness has to win.
This whole deep dive, from non-stationarity all the way to GPU failures, it really all boils down to one thing: radical transparency. The sources argue that code and compute ledgets have to be treated as first-class scientific artifacts.
They absolutely do. They're not footnotes, they are part of the experiment itself, which is why we need a non-negotiable reporting checklist for all DRL publications.
Let's walk through the 5 mandates for rigor that the sources lay out. Number 1, the absolute basic: code and environment.
Provide linked executable code, all dependencies, all versions, and a read.me with the exact command line instructions to reproduce your main figure. No guesswork allowed.
Second, experimental setup. This gets at that algorithmic brittleness problem.
You must disclose the full hyperparameter search range you explored, not just the final settings. And crucially, you have to state the method you used to select them. Was it a grid search? Random? Manual tuning? That context is vital.
Third, statistical rigor. This is about killing the lucky seed.
Report the exact number of independent runs, 10, 20, whatever it is. And you have to present the results with a measure of central tendency, the mean, and a measure of variation, like a 95% confidence interval.
Fourth, and this one could be controversial, computational budget.
Yes. You must include the full training curves, specify the hardware, the wall clock runtime, and the estimated energy cost.
The energy cost, why?
It's about computational accountability. We need to be able to tell the difference between a genuinely smarter algorithm and one that just got better results by throwing 1,000,000 GPU hours at the problem.
So it contextualizes the improvement. If algorithm A is slightly better but took 10 times the energy, that's a critical part of the finding.
It's a huge part of the finding. And finally, number 5, determinism control.
You have to spell it out.
You explicitly document every single step you took to mitigate non-determinism, from GPU settings to your parallelization strategy. If you can't guarantee determinism, you can't guarantee anything.
These 5 mandates, they really do form the pillars of a more robust DRL. You've got technical control, architectural rigor, and methodological standardization.
The problem is clear. DRL is inherently vulnerable because of non-stationarity and all these hidden sources of variance. But the solution isn't just about building a better algorithm. It's about building better science, a culture of real transparency.
So what's the final thought here for you, the listener, who might be working in this field? What does this future look like?
It means we have to transition from systemic variance to robust generalization. The goal has to shift away from this frantic hunt for a single lucky peak score that only works in one lab. Instead, the goal becomes building policies that have higher generalization skills and work reliably everywhere, on anyone's machine. Adopting these standards, it's what separates real scientific progress from what is, at the end of the day, just lucky noise.